Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. The question itself that Parash posted on the forum, I've never seen a question quite like it on the GMAT. So this is not, as far as I can tell, it is not representative of a real GMAT question, but I thought it was a good question to get our brains thinking deeply about what an LCM means. So I guess before we actually try to solve this question, we should talk about what is a least common multiple and how to think about a least common multiple. So if I take, say, the numbers 15 and 18, just as an example, and I want to find the least common multiple of those two numbers, one way to do that is to look at the prime boxes of those numbers. So the prime box of 15 I have here, prime box of 18 I have here, and now as I construct the prime box of the LCM of those numbers, what am I going to ask myself? I want it to be the least, right? That's what the L stands for, but I also want it to be a multiple of both. That's what the C stands for, common multiple. So we're looking for a number that on the one hand is as small as possible. So I want to try to minimize the contents of this LCM box, but I can't just make it empty because then it won't be a multiple of anything. And I do need it to be a multiple of those numbers of 15 and of 18. So I ask myself, well, is it absolutely necessary to have any 2's in the prime box of the LCM? And why am I asking about 2's? I like to go in order. 2 is the smallest prime number, and after that I look at 3's, 5's, 7's, 11's, 13's, and so on. I like to be organized. So I ask myself, is it absolutely necessary to have any 2's? And the answer is yes, it is necessary, because without any 2's, I won't be a multiple of 18. How many 2's must I include in the LCM? Well, it looks like 1 2 is sufficient. I don't need more than a single 2 because, well, looking at the prime boxes of 15 and 18, 1 would be enough. And then next I go to 3's. Is it necessary to have any 3's? Yes. But what's the minimum number of 3's that are necessary in order for this box to be a multiple of each of those numbers?
2.
Exactly. 2 3's would be enough. In fact, it would be more than enough to be a multiple of this one, but it would be just enough to be a multiple of this one. So it's the minimum number of 3's that would make me a multiple of each of those numbers. Okay, next up are 5's. Are there any 5's necessary in this box? The answer is yes. I do require at least one 5 in order to be a multiple of this guy. So that's the minimum number of 5's that I need. And guess what? We're done. I'm not going to need any 7's, 11's, 13's, and so on. So that's kind of how we think about an LCM. And you might say, Avi, that was a really awkward and time-consuming way to find the least common multiple of 15 and 18. An easier way would have been to just start looking at multiples of 15. So 15, 30, 45, 60, 75, 90, and stop when we get to a multiple of 18. I think that's how we learned to do this in grade 4 when we were learning how to do a common denominator when adding and subtracting fractions. But the problem with that method is it doesn't scale to more difficult situations where the numbers are bigger. Whereas this method with the prime boxes, that you could do with any numbers, even very large, complicated numbers. So I think also this method with the prime boxes also helps us conceptually understand on a deeper level what an LCM is, and hopefully that will help us in trying to solve this question. You started out quite well. I'm going to help you take that a little bit further. I think the key to thinking about this question is the realization that this x and this x is the same x. They're the same number. I think that's really important because while I don't know what x is, I do know, as Parash mentioned, that it has a 2 in its prime box and it has a 3 in its prime box, because otherwise these wouldn't be integers. We know that these are positive integers, so x must be even, and also x must be a multiple of 3. So what I'm going to do now is kind of imagine a prime box for x that has at least 1 2. I'm just going to put a square there for the exponent, because I don't know how many 2's there are, but there's at least 1. Same goes for the 3's. There's at least 1 3. And then there may or may not be other stuff. And I haven't yet used the fact that we know the LCM. And we know the LCM is 210. I haven't used that yet. But when I ask myself, if this is the prime box of x, what does the prime box of this look like? Well, it would look exactly the same with 1 fewer 2. So however many 2's there are in x, this will look identical except 1 fewer 2. So it'll still have that 3 to whatever that was. It'll still have the ... In terms of the 2's, it'll have 1 fewer. Let's do a -1 there to kind of show it. It'll just have 1 fewer 2 compared to the original number. And what about x over 3? What would that look like? Same idea, except 1 fewer 3. So here I'll do the -1 for the 3, and there's a ... So it's the same exact number, except one of them has 1 fewer 2, and the other has 1 fewer 3. Otherwise, they're identical. Now, still, before we look at the number 210, because I think we're not quite ready for that yet, let's do a little bit more thinking. What could we say about the LCM, just in general, just abstractly speaking? What can we say about the LCM of these two numbers, given that those two numbers are almost identical, right? One of them has an extra 2 and the other has an extra 3 relative to one another in the prime boxes, but otherwise they're identical. So would you expect their LCM to be a lot bigger than they are, or not a lot bigger? Or how would you think about it? The LCM can't be smaller than the numbers that it's supposed to be a multiple of, because if you're a multiple of something, then you're at least as big as that thing. I think you're saying the following: look, guys, if we want a number that is a multiple of this and also is a multiple of this, we could think about it in the following way. We could think about it in steps. First step, we'd want it to just be a multiple of that. So what's the least number that is a multiple of that? Well, it would be that, x over 2. That's the least multiple of itself. Is that also a multiple of this? And again, remember, we were comparing these two boxes and we were saying, well, this box has 1 extra 3 compared to this one, but this one has 1 extra 2 compared to this one. So if you have a number that's already a multiple of this, because it is this, what extra stuff would you need in order to make it also a multiple of that, given that the difference is you have an extra 2 here? So you have a number that's a multiple of that. What more would that number require in order to also be a multiple of this guy, when we know that this guy has an extra 2 but is otherwise identical?
I mean, we could, I guess, the extra 2.
You got it.
Yeah, we could do the thing you were doing in the beginning. We could say, all right, let's start with 2's. What does the LCM need? And you see the highest 2 there is from the bottom box. Then you go from 3. See the highest 3 is actually the top box. And you keep going and you see the ...
And the ... is identical, so therefore you just have the ... and that would fit both of those. Now, I see that not everyone is following along, so let me take a numerical example to make it a little bit less abstract. So let's imagine that x is 30. So if x is 30, this is 15, this is 10. And the prime box of x over 2 is 3 to the 1, 5 to the 1, and the prime box of x over 3 is 2 to the 1, 5 to the 1. So we can see that this kind of matches what we had earlier, right? Because the prime boxes are identical, except one of them has an extra 3 compared to the other, and one of them has an extra 2 compared to the other. And so if we're looking for the LCM, we could say, well, let's just take this number, because this number is a multiple of itself, and then ask ourselves, what else would we need to give that in order for it to also be a multiple of this number? Well, The numbers are identical, except this one has an extra 2. So just take the left number, give it an extra 2 to the power of 1, and now you're good. Now you have the LCM. Now you have a number that is a multiple of each of them. There's an analogy that I use there, and I've used it in an AMA late last year, late 2020, where I talked about the inventory of jackets of different sizes at a clothing store. So they have jackets size 2, size 3, size 5, size 7, size 11, size 13. And those are the different sizes that are available for jackets. And there are different numbers of jackets of each size. So maybe you have 5 jackets size 2. So the analogy would be a prime box where you have 2 to the power of 5. Maybe you have 3 jackets size 3 and 2 jackets size 5 and 10 jackets size 7. That's the inventory. And then I said that the LCM is you had a customer coming in today and you don't know exactly what he's going to want to buy, but you know that it will be one of 2 shopping lists. He's either going to want to buy the prime box of this number or he's going to want to buy the prime box of this other number, but you don't know which. What's the minimum inventory you need to have on hand to ensure that you'll be able to satisfy the customer without knowing which of the 2 shopping lists he's going to come in with? So that's the analogy that I came up with for LCM in my book and in one of the previous AMAs. So just to give you a visual, in case you're a visual learner, let's take this example, 50. So prime box is 2 to the 1, 5 squared. And let's say 75. So that's 3 to the 1, 5 squared. So I have a customer, I know he's going to be coming in today. I don't know which of these shopping lists he's going to come in with. He's either going to want to purchase 1 jacket size 2 and 2 jackets size 5, or he's going to want to purchase 1 jacket size 3 and 2 jackets size 5. So one way to look at this is you can say, I know for sure he's going to want 2 jackets size 5. That I know for sure. But what I don't know for sure is if he's going to want the single jacket in size 3 or in size 2. That's where I have some question marks. The LCM is me, the retail clerk or the store owner, me trying to figure out the minimum amount of inventory that I require on hand to ensure that the customer will be happy. So I'm not going to need any jacket size 7, 11, 13, 17, 19. I don't need any of those. I'm trying to minimize the amount of inventory that I have, but I will require 1 of these, 1 of these, and 2 of these. That's the minimum inventory that I need in order to make sure that the customer will be happy. That's another way to think about LCM. We're told that this is a shopping list, and this is a shopping list, and we don't know which of those lists the customer will come in with, but we know that the minimum inventory that we're going to need in order to service this customer is this, because that's 210. And then the question is, what is this customer's ideal shopping list? What is X? If the customer will be satisfied with 210, in other words, with 1 jacket of each of these sizes, 2, 3, 5, and 7, in order to be a multiple of X over 2, at a minimum, you're going to need X over 2. At a minimum. The problem is you also want to be a multiple of X over 3, and guess what? X over 3 will contain that 2 in the X. How do I know that there's a 2 in the X? Because otherwise this wouldn't be an integer. And vice versa. You could say, yeah, X over 3 is a multiple of X over 3, but I'm also going to need that 3 because of the X over 2. So it turns out that X must be 210. At most, since we know that this is a multiple of this, we can say that at most X has this, and no ... This is the most that X could possibly have. I'm not saying this is X, I'm saying just from the fact that 210 is a multiple of half of X, at most X is this. By the way, X could be 1. No, not 1. X could be 2. Just from looking at this part, just from saying 210 is a multiple of X over 2, X could be 2. So at most x is this, at least x is 2. Just from looking at that part. And then separately, we'll say just from looking at this part, just from knowing that 210 is a multiple of x over 3, at most, what can we say about x? At most, it's
2 times 3 to 2.
Yeah.
5.
At most. And at least it's 3. And at most it's this. Now, how do you reconcile the fact that on the one hand, x has at most 2 squared, and on the other hand, x has at most 2 to the power of 1? Who's right? Who's lying? Well, neither of them is lying. They're both telling the truth. But if they're both telling the truth, then what would you say? Would you say that at most there's 2 of them, or at most there's 1 of them, if they're both telling the truth?
At most 1 of them.
At most 1, yeah. Because this guy is saying that at most there's 2 of them, he just didn't know the full picture. So he said, yeah, at most you could have 2 of them. But this guy knows better. He's like, oh, actually, at most you can have only 1.
He's more precise.
He's more precise, exactly. It's like saying that, x is greater than 10 and x is greater than 5. These can both be true at the same time. But if the second guy is telling the truth, if the first guy is telling the truth, if that guy is correct, then this is just not giving us the full picture. It's just not as precise. So we have a stronger statement there. So it's that kind of logic. And same goes for the 3 squared and 3 to the power of 1. How do you reconcile? If one person tells you, well, there could at most be that many 3s, but the other person tells you, well, there's only at most that many 3s, you go with the more precise, the narrower range. And that's how you end up with, okay, therefore x at most is this, but also at least it's this. Why at least? Because otherwise, the least common multiple wouldn't be 210. It would be something smaller. It would be just 70 or 30 or 10 or something like that. The more useful a statement is, the more it narrows the range of possibilities. Or another analogy is saying to you, I'm in Canada, versus saying to you, I'm in Toronto. They're both true. But the narrower range, Toronto, is more precise. It gives you more information. NG, I'm offering you a job, at least $10 per year. Well, what do you say? Will you take the job or not? What do you think?
Depends on what I'm making.
I think it would be a mistake to say no. I think it would be a mistake to say no. Why? Maybe I'm planning to pay you $1 million a year, right? Mm-hmm. This would still be true. Even if I'm planning to pay you $1 million a year, this is still true. Now, I could also say, NG, I'm offering you a job in which I will pay you at least $100 per year. Now, is it possible that these two statements are both truthful?
Yes.
Yeah, it's possible. And which of these statements would you say is the more informative statement? The second one. Yeah. The second one gives you more information. Why? Because it eliminates a range of possibilities between 10 and 100. Now you know, thanks to the second statement, that I'm not planning to pay you $20 a year or $30 a year or $90 a year. Okay, now let's look at another story. I promise you that if you play ice hockey, you will lose at most 5 teeth. So that's giving you some reassurance, right? You're not going to lose all your teeth if you play ice hockey. Maybe you won't lose any, right? But at most, I'm giving you an upper limit. At most, you'll lose 5 teeth. Now I'm giving you another promise. If you play ice hockey, you will lose at most 2 teeth. So how is it possible that both of these promises are true and both of these promises will be kept? Is it possible they're both telling the truth?
Yes.
Yeah, it's possible. But if you end up losing 4 teeth, well, then one of the promises wasn't kept.
Mm-hmm.
So if both promises are to be kept, then what? Then this must be true. The only way that both promises will be kept is if this promise is kept. The minute this promise is kept, automatically the other promise is kept as well, but not the other way around. why is it that x is definitely 7,560 in this case? It's for the same reason that in the original question, x was exactly 210. And what is that reason? Or what is the important point here? It's that 2 and 3 are they have nothing in common. Their GCF is 1. So these are distinct prime numbers with no commonality. And so when you say, I take these identical numbers, they're exactly identical with one exception, right? One of them has one fewer 2 and one of them has one fewer 3, but otherwise they're exactly identical. And you're starting to talk to me about their LCM. What I'm thinking is, well, if they were identical, the LCM would just be the number itself. Like if we're talking about x and x, the LCM would just be x. Okay, but what's the difference here? Well, in one of them we're missing a 2 and in the other we're missing a 3. And I'm thinking, well, the LCM would still be x. Why would it still be x? Because you're still going to need the 2 for the one of them and you'll still need the 3 for the other one of them. So the LCM won't be missing either the 2 or the 3 because you'll need it for the other guy. Because on the one hand you have x over 2, and the other hand you have x over 3. For one of them you'll need that extra 2, and for the other you'll need that extra 3. So in the end of the day, the LCM will just be x. And so that would be true for any number, whether it's 210 or 7560. We can say in general, and this is not a takeaway to memorize, of course, this is a takeaway to understand, but we can say in general that the LCM of x over 2 and x over 3 is always equal x. This is always true. And we can generalize that even more. We can even say the following. The LCM of x over a and x over b, if GCF of AB is 1, so the LCM is just x. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below. And give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. X over 8 and x over 4. And you say, okay, I want a number that is a multiple of both of those, but I want it to be the least. So what's the least number that is a multiple of both of those? And I would say, well, isn't it true that x over 4 is a multiple of x over 8? Isn't that true? Think about that. X over 4 is exactly twice x over 8. So if one of them is already a multiple of the other, then that's the LCM. The LCM of those is x over 4. That's why it matters.
Yeah, because if x if it's 24, and you're right, the LCM is 6, which is indeed x by 4.
But you understand the reason why this co-primes thing is important? This only works if the denominators there are have no GCF. The GCF is 1. So let's talk about that for a moment. Now, x over 12 is not a multiple of x over 8, and x over 8 is not a multiple of x over 12. But when we talk about their LCM, we can still find a number smaller than x that is a multiple of both of those. What is that number? I think it's x over 4. Check me. Is x over 4 a multiple of x over 8? Yeah, it's double. It's double x over 8. Is x over 4 a multiple of x over 12? Yeah, it's triple. So this is true. X over 4 is a multiple of x over 8, and x over 4 is a multiple of x over 12. Now, I haven't proved yet that it's the least common multiple of those, but it's certainly less than x. So I've proved that x is not the LCM, because x over 4 is smaller than that, and it is a common multiple. Now, if you're curious about how I came up with x over 4, think about what's the GCF of 8 and 12.
4.
Ha! So now we can make an even more generalized conclusion. If you have x over a and x over b, their LCM is always going to be x over GCF AB, where a and b are positive integers. A, b, and x are all positive integers, and also x over a is a positive integer and x over b is a positive integer. So those are the conditions. But this is always going to be true. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.